Martin and I are doing on your own 13.3. Martin, please read it to me.
In acetylene torch, C2H2 is burned to make the hot blue flame that cuts or welds metal. Assuming that the combustion is complete, what is the delta H of this reaction?
Okay. So acetylene plus oxygen yields carbon dioxide and water. That's the equation for complete combustion. This equation is not balanced. Let's balance it as quickly as we can. So we want at least 2 of these because we need 2 carbons. Now we have 4 oxygen. We definitely want an even number of oxygen. So we're going to have 2 here. That gives us 6, which makes 3. Now we need more of these because of that. So that means 2. That's 4. So we need at least 4 of these, which gives us 8. 5. Okay, so we have 2 C2H2, 5 O2, 4 CO2, and 2 H2O. Okay, that's our balanced equation. Now what do we need to do in order to calculate the delta H?
No,
we need to know what kind of bonds we're talking about. Why?
Because then we can do subtraction.
Yeah, we'll add up the bond energies on this side of the equation. We'll subtract the bond energies on this side of the equation, and that will give us our change in enthalpy, our delta H, right? So what does carbon look like? Carbon has how many electrons?
7.
It does?
Oh, wait, no, it only has 4.
Yeah, so where's carbon? Carbon is in column 4A. It has 4 electrons. And hydrogen is in column 1A. How many electrons does it have?
1.
So what's going to happen with these carbon and hydrogen? These guys are going to form a bond, right? And these guys are going to form a triple bond.
Yes.
Okay? So it probably should look like that. All right?
Yes.
So here's that. What's the oxygen going to look like? How many? Where's the oxygen? Oxygen has how many electrons?
6.
6. So it's going to go right? And it's going to double up there, right?
Yeah.
So it's going to have a double bond there. How about the carbon dioxide? Carbon, you said, has 4. Oxygen has 6. We're going to end up with something like that, right?
Yes.
What about the water?
Hydrogen and oxygen. H and O is 459.
Good. So that's what our Lewis structures look like, right?
Yes.
Okay, the combustion is complete. All of this reacts with all of this. So now we have to look at the bonds. Which bonds need to be broken?
The ones on the reacting side.
Yes. Okay, so how many we look at table 13.1 and we get the bond energies. What is the bond energy of this bond? triple bond,
That's 835.
kilojoules per mole.
Yes.
How about this bond?
CH is 411.
Kilojoules per mole. How about this bond?
Double bonded OO is 494 kJ/m.
And how about this bond?
OC double bonded is 799 kJ/m.
And these bonds.
OH single bonded is 459 kJ/m.
Alrighty. Now, what do I do next?
Now we multiply them by their number of moles and then subtract one side from the other.
Okay, so what have I got here? I've got 2 moles times 835 kilojoules per mole.
Yes.
Plus what?
Plus,
About 2 times 2 moles.
Okay.
Of what? Of 411 kilojoules per mole.
Yes.
Plus what?
Plus 5 times
494 kilojoules per mole.
Yeah.
And that should be 5 moles. Okay, is that all for my reactants side?
Yes.
Okay, so I'm going to subtract the products side, which is
4 times 700. 4 times 2.
2 times 4 moles.
8 times 799
kilojoules per mole.
Minus
Plus.
Okay. 4 times
2 times 2 moles.
459 kJ/m.
459 kilojoules per mole. Okay, mole. So,
And we plug in those numbers and we come out with negative 2,400. Okay.
can you show me the work that you did on all of this or not?
Sure.
So 5,784 kilojoules minus 8,228 kilojoules. And so that gives us, what is it, negative
2,444 kilojoules. exothermic.
It generally is when you're burning stuff.
Yeah.
Thank you, Martin.